Let's start this video by review the correlator receiver. At the receiver, the received signal is multiplied firstly by the base function. Then we integral the signal. We obtain y of t, and then we sample the signal at the end of the pulse duration tb. Now let's look at a special case that we do not have noise at the receiver, which is the ideal case. The noise is equal to 0. Then RT, the received signal, equals to the transmitted signal. This is a geometric representation of the pulse transmitted. And at the output of the integrator, we do the integral from 0 to t. We use dummy variable tau. So this is r tau. Sm is a scalar. We take it out. Cosine t has this format, is rectangular. This integral equals to Sm from 0 to t. This t, small t, is in between 0 to tb. And the value of cosine tau squared, that will be square root 1 over tb squared, d of tau. This equals to Sm 0 to t, 1 over tb, and d of tau, that equals, this is what I obtained here. Now, if digital 1 is transmitted, Sm equals to square root EB. So this integral equals to square root EB multiplied by 1 over TB multiplied by small t. If digital 0 is transmitted, Sm is equals to minus square root TB. Therefore, the integral equals to minus square root EB multiplied by 1 over TB multiplied by t. Now, if we look at the graph, if digital 1 is transmitted, this is a linear function. The slope is positive, so the output at the integrator is increasing linearly. At time tb here, it reached the maximum. After tb, this time instant, this phi of t equals 0, so the constant here. Now, if digital 0 is transmitted, the slope is negative. So it's decreasing linearly. At time tb, at time equals to tb, it reached the minimum. At the output of correlator, we sample at t equals to tb. We look at the value of the correlator at tb, is at the tb. This is optimum. This integral reached the maximum point if digital 1 is transmitted, and the integral reach the minimum point if digital 0 is transmitted. Because the integral accumulating the values with time, to make sure the receiver works properly, we need to reset the integrator to 0 at every TB. At the end of each pulse, we need to set it to 0. Otherwise, the integral won't start with 0 here. If we do not reset at the end of each pulse, if 1, 1, 1 keep coming, if digit 1 keep coming, and this integral will go. So therefore, eventually this integrator will saturate it. That's one thing. The other thing is we cannot detect the value. Or if this 101 is transmitted. Now, if it's 1 is transmitted, next negative square root EB come in, and then this integral will be decreasing because of the negative slope. Next one, if it is 1, it becomes positive again. So in this case, there's no way, even though we sample at TB, we cannot detect the correct bits. Therefore, it is required that correlator receiver has to be reset to 0 at the end of each bit interval TB. This receiver is also called integrate and dump filter. And this receiver is also called match filter receiver. That's the other name for this receiver. Now let's look at one important property of the correlator receiver, that's the signal-to-noise ratio. Signal-to-noise ratio is a very important factor in communication systems. Signal-to-noise ratio, by the name, is defined as the ratio of the power of the signal and the power of the noise. So PS is a signal power, PN, that's the noise power. Noise power is expectation of n squared because of the zero mean here, the zero mean in the noise. Let's look at the SNR for the correlator receiver. At the correlator, the output is at this point. So at TB, T equals to TB, small t equals to TB, then this point equals to square root EB divided by TB, and small t equals to TB, and this equals to square root EB. If digital 0 is transmitted at TB, this value is equals to minus square root EB 1 minus TB multiplied by TB, that equals to minus square root EB. So therefore, we can see at the output of the correlator at TB, the signal power either is plus EB or minus EB. So we take the square, that's the signal power. And then what is the noise power? The noise power is n naught divided by 2, and this is the expectation of n squared we derived in previous video. This equals to EB n naught divided by 2. And this is the signal to noise ratio for this correlator receiver. It turns out that the signal to noise ratio is maximized for this correlator receiver. This is exactly what I said. The signal to noise ratio at output of the correlator, that's equals to SM squared. SM squared, SM equals to plus or minus EB, and this equals to EB divided by N naught divided by 2. And here I summarize that at the output of the correlator, the output equals to ESM plus EN. EN is the noise, which is Gaussian. And this term, that's the signal term, it can be justified from here. This is a signal term without noise. So at T, at this small t equals to TB, they support at TB, small t equals to TB, that cancel out each other. So therefore, at TB, the output of correlator equals to ASM. And this is exactly here when digital 1 is transmitted. And this is SM. This is S1, the coefficient when digital 1 is transmitted. This is S2, the coefficient when 0 is transmitted. These coefficients are the geometric representations.